This is the exam review for Module 2, which included aldehyde ketones, carboxylic acid derivatives, and carbohydrates. So question 1 says, what is the name of this compound shown? And when we look at it, we can see we have 4 main functional groups. We have a carboxylic acid, a 4-methyl group or aldehyde group, an alcohol, and a bromide. So we have 4 functional groups. The highest one gets priority. So that's going to be the carboxylic acid, which is at oxidation state 3. The aldehyde's at 2. The alcohol's 1. The bromide's 1. So again, that's oxidation state analysis. That determines what the suffix or the parent of the compound is. So it's going to be an acid. And then the longest chain, we can circle that. Has to include the acid. So that's 4 carbons. It's going to be a butynoic acid. So that has to be in the name. And then we just march down the chain. So we have an aldehyde or 4-methyl group at position 2. We have a hydroxy group at position 3, and then a bromo group at position 4. So those go in alphabetical order. Not numerical order, but according to the alphabetic order of the substituent, and then the numbers are attached to those substituents. So C is the correct answer for that. Question 2 goes in consideration of the structure of question 1. What is the total sum of the oxidation states? So we had just done that. We have an acid, which is 3, plus an aldehyde, which is 2, plus an alcohol, which is 1, plus a bromide, which is 1. So that gets us 3 plus 2 is 5, plus 1 is 6, plus 1 is 7. So this is A. Question 3, which of the following is the C4 epimer of glucose? So we know that glucose has all equatorial substituents. So we know that C1 is the anomeric carbon. So we count from there 1, 2, 3, 4. D is the C4 epimer, and that's called galactose. Question number 4, what is the relationship between the structures A and B in question 3? So they are epimeric at C1, and when it's at C1, we call those anomers. So this is D. Question 5, what is the name of the C1 functional group in structure A of question number 3? That's a hemiacetal, and again, that structure has O carbon, OH, and then 2 carbon substituents. So that's sort of a general representation of what you're looking at there. So that's a hemiacetal in that form. Question number 6, what is the pK of the most acidic functional group in the product when D-glucose is treated with nitric acid? So we're oxidizing to the carboxylic acid, so that has a pK of 5, so that's A. 7 says, what is the product when methylcyclopentane is treated with the following sequence of reagents? So the answer for this one is going to be C. So we're ending up with a ketal, and what we're doing essentially is taking methylcyclopentane, we're doing a bromination, then an elimination through the Hoffman with the large base, then ozonolysis with reductive work up to the ketone, followed by ketalization under acidic conditions. Question 8, the aldohexoses D-glucose and D-mannose are derived from the aldopentose D-arabinose via the Kiliani-Fisher chain elongation sequence. Which of the following is the C2 epimer of D-arabinose? So this one's going to be C. So we know that glucose is equal to right, left, right, right when we're going down the chain. So arabinose must be left, right, right. So the C2 epimer of that must be right, right, right. So that's how we get these substituents all on the right side, so that's C. Question 9, what is the product of this reaction? So you're treating it essentially with acid. So what we're going to do here, we have oxidation state 2, we have oxidation state 1. This is going to cyclize, and we're going to end up with essentially what is D, and again, that's a hemiacetal. So we have that oxidation state preservation from the ketone to the hemiacetal at this point, and that's just a cyclization. So question 10 was the mistake here in terms of what the question was, but it's what is the product of this reaction? So you're treating it with lithium aluminum hydride and then doing an acidic workup. So you're at oxidation state 3 here, you're at oxidation state 1 there. The 3 is going to 1, so you're going to end up with B as your final product. Question 11, we want to convert pentanal into the primary amide. So what we need to do, this is at oxidation state 2, this is 3. We need to treat with MCPBA. So that generates the oxidation state 3 from the acid via migration of the CH bond. Need to convert that into the acid chloride, maintaining oxidation state 3, and then we treat with dimethylamine. And so, we treat with sodium amide and ammonia. And so for 11, we end up with C as the correct response. These symbols here didn't translate in the PDF. They should be arrows. That's what those mean. Question 12 is asking what sequence of reagents will take 1-butanol to 3,3-dimethoxyheptane. So we're starting at an oxidation state of 1. And we're ending up at an oxidation state of 2. So the correct answer for this one is going to be A. We basically need to do an oxidation to the aldehyde, then do a Grignard addition, to add in the 2 carbons, then do another oxidation to the ketone. And from there, we treating with the acidic methanol, and that generates the acetal, or in this case, the ketal. So what reagents will convert a reducing sugar into a non-reducing sugar? For 13, and this is B. So again, so a reducing sugar looks like the following, where it has a hemiacetal, and you're doing an acidic exchange of that OH group for another alcohol. So now it's an acetal. So again, the OH is converted to O carbon, and that's a reducing sugar. The reducing sugar is converted into a non-reducing sugar through that reaction. Question 14, what reagents will achieve the following transformation? So this is an aldonic acid synthesis. So we have A, which is bromine water, is what we learned to oxidize the aldehyde into the acid for the sugar chemistry. Starting from D-glucose, what sequence of reactions will carry out the preparation of the fully protected sugar is shown. So this is sequence A. So the anomeric C1 we need to treat with isopropanol under acidic conditions. Now we have the 3 remaining alcohols. We have 1 primary, 3 secondary. So the primary is going to go first, so that's the acetylation with acetic anhydride. And then finally the last 3 secondary alcohols, that's where we do the Williamson ether synthesis by treating with sodium hydride and then benzyl bromide. So that's about sequencing in terms of differentiating the different alcohols present in D-glucose. So for the spectroscopy question, A is an acid chloride, and we know that because we're dealing with a signal at 1800. B, we have a carbonyl less than 1700 along with this doublet, so that is basically the primary amide. 16 is saying, in consideration of the 4 IR spectra shown above, which spectrum would be observed when a compound with spectrum A is treated with ethanol? So A. So C, we have your typical, so 17, we'll say 1750 carbonyl stretch, that's going to be an ester. And then D, we have this signal around 2200, that's going to be a nitrile. So A or 16 is asking you A plus ethanol, that's giving you an ester. So this answer is C. 17 is asking you a spectrum B plus phosphorus oxychloride. You're taking a primary amide plus a dehydrating agent, that's giving you a nitrile, so that's D. In consideration of the 4 IR spectra shown above, which spectrum has a functional group of 2 oxygens, that's an ester, so that equals C. In consideration of the 4 IR spectra shown above, which spectrum will be observed when a compound of spectrum A is treated with ammonia? So that's an acid chloride plus ammonia. That's going to give you a primary amide. So that is B. And then finally 20, what spectrum results when 3-pentanone, so that's 3-pentanone, it's a ketone, is treated with MCPBA followed by hydrolysis and then thionyl chloride, so that's going to give you spectrum A. Again, you're doing a Baeyer-Villiger, then you're doing a basic saponification, an acidification of the carboxylate, and then transforming that into an acid chloride. 21 says, what sequence of numbers demonstrates the arrows for the elimination that takes place during a Fischer esterification? So you're forming an ester, So you need to draw an ester as the product. And the what is set up here is essentially the oxygen that's doubly protonated is going to leave. So because you need to form an ester, the arrow has to start at 6. So 6 to 3, 6, 3, and then you're eliminating 5, and that's going to 0, 5, 0. So you're ending up with plus your water. So that's the elimination that's taking place. 22 says, what sequence of numbers demonstrates the arrows for activation of oxalochloride by DMF in the conversion of an acid to an acid chloride? So one arrow has been drawn to help you out. So if we're forming a nitrogen-carbon double bond, we have to break carbon-oxygen pi bond 1. So we're going to break that, and it's going towards the electrophilic center of oxalochloride, which is the carbonyl. So 1 to 4, and then we're going to break the pi bond 3 to 6. So that would be the product of that step in the sequence. So this is 1, 4, 3, 6. What sequence of numbers demonstrates the arrows for the migration event that takes place in a Baeyer-Villiger reaction after the indicated arrow collapses to reform the protonated carbonyl? So at this point is the migration. So you're reforming this protonated carbonyl. So what you have to do is make the choice of the alpha carbons, which one's going to migrate. You have a methyl group, versus a tertiary alkyl. So the tertiary alkyl is going to win. So from there, that bond, again, the odd numbers are the bonds. 3 is going to attack 6, and then 7 is going to break to form a bond with 8, or to put electrons on 8. So 3 migrates over to 6, 7 goes on to 8. 3, 6, 7, 8. And what you're ending up with again, now you formed that ester, and then your byproduct is that benzoate anion. 24 is asking you what is the sequence of numbers that demonstrates the attack of the Wittig reagent on the aldehyde. So the negative charge is on 8, so it has to start at 8. We know from a nucleophilic addition to a carbonyl, the carbonyl carbon's positive, so 8 to 2, and then 5 to 0. We end up with that intermediate that will subsequently collapse to form the alkene. Finally, 25, we want the nucleophilic addition of cyanide anion to the carbonyl of D-glyceraldehyde is the first step in the Kiliani-Fischer. So it's telling you nucleophilic addition of cyanide. So 6 is the start, 6 to 0, and then 5 to 2. So that's giving you the cyanohydrin, as that initiating step in the chain elongation reaction. Excuse me, this should be 5-2. 6052. So that has been a screencast review of Module 2 exam for the Spring 2022 semester of Organic Chemistry 2.